All right, should we take a look at this one? All right, so we're going to let x equal which of the three trig functions? Sine, tangent, or secant? Secant. I know if I looked at this, it'd be like automatically I'm ruling out tangent because there's not a plus sign, and tangent starts with the t, which is like a plus. So it's either secant or sine, and I know it's not sine because if you get sine squared minus 1, that's negative cosine squared, which is not helpful. So we know that our trig substitution is x equal to secant theta, and our dx is secant theta tangent theta d theta. So we just start replacing things. So this is going to equal the integral of the square root of, now this is where you can kind of do as much or as little work as you want, as long as it's clear. If I was doing this on a test, I would probably write this first step and be like, okay, it's going to be secant squared theta minus 1 over secant theta times secant theta tangent theta d theta. And I'm going to start canceling things. Cancel the secant. And then depending on your comfort level, secant squared theta minus 1 is tangent squared. So you get the integral of the square root of tangent squared theta times tangent theta, which is then going to be the integral of tangent squared theta, which is real tricky until you know the trick. And then once you know the trick, you're like, oh yeah, it's super straightforward. Tangent squared is just secant squared theta minus 1. The antiderivative of secant squared is tangent. The antiderivative of 1 is theta. And then we have to change back to being in terms of x. So we draw a little triangle. I didn't really do one like this where it was 1. So if you have just x equal to something, it's not like 3 secant theta or 5 secant theta. You just say it's x over 1. So we're going to say that, oh yeah, secant theta equals x over 1. I never remember what secant is. I always be like, okay, cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent, right? Really, like that's how I'm thinking of it. So then draw my triangle. Secant of theta is hypotenuse over adjacent. And I hope we talked about this last time, how the third side is always going to be whatever was in your integral. So the third side is going to be the square root of x squared minus 1. It always works that way. It's kind of great. You can also use the Pythagorean theorem, and you should be able to use the Pythagorean theorem to see that. So then we rewrite this as tangent of theta, which is opposite over adjacent. So square root of x squared minus 1 minus theta, which is the arc secant of x, or the inverse secant if you prefer to write it that way. And that's the whole story. Yeah, that's it. Okay. Did I blow it? But tangent is opposite over adjacent, right? I don't know. You take a look.
Oh,
you put your one in the wrong spot. Yeah. One thing I wanted to say about this, because I thought it was kind of interesting, or one thing to consider. Let's say we have the same problem, but it was a definite integral. If I was given the definite integral from, say, 1 to root 2 of the square root of x squared minus 1. One option would be to do all the same work we did. So if I had to do this, one way I could do it, be like, okay, I'm going to do the whole integral over here. I'm going to get the square root of x squared minus arc x minus 1 minus arc secant of x, and then plug in my limits of integration. So one option would be to say it's this antiderivative from 1 to root 2. And you can plug in and figure out your answer. So we're going to get, let's see, the square root of the square root of 2 squared minus 1 minus the arc secant of the square root of 2 minus the square root of 1 minus 1 minus the arc secant of 1. Okay, fun questions. Well, not so fun. Square root of 2 squared is 2. 2 minus 1 is 1. So you get 1. What's the arc secant of root 2? 5/4 indeed. And then minus 0 minus the arc secant of 1 is, it is 0. Right, the angle whose secant is equal to 1. So you get 1 minus pi/4. Now the reason I mentioned this is because if you hadn't already done the antiderivative, you might not do it this way. What I mean is, if we started with the integral from 1 to root 2 of the square root of x squared minus 1 over x, and did the trig substitution like we did before, which I'll just kind of reference up here. And there was a trig substitution. We could rewrite this as the integral of tangent squared. Right, that was what we got after we did all the simple. Oh, wow, that looks really terrible. Sorry. Integral of tangent squared d theta. And our limits of integration, we could change them. So this is an x value, but it's kind of weird. It's kind of like the reverse of a u substitution. So if you change limits of integration, you have to say, okay, x equals 1, so secant of theta equals 1, so theta equals 0. And x equals root 2, so secant of theta equals root 2, so theta equals pi over 4. Which kind of feels backwards to me, but it works. And then you can plug in your limits of integration to be from 0 to pi over 4. And then you can finish the problem this way. You can say it's going to be the integral from 0 to pi over 4 of secant squared theta minus 1 d theta. And then that's going to be tangent theta minus theta from 0 to pi over 4. You get tangent of pi over 4 minus pi over 4 minus tangent of 0 minus 0. And that's exactly equal to 1 minus pi over 4 minus 0 minus 0. So you get the same answer either way of doing it. It just kind of depends on how you want to see it. I feel like there's not a better option here. I feel like this is perfectly fine to do it this way. It might be how I actually do it. It might be perfectly fine to do it this way. I would say I would only really consider changing limits of integration though, if they made sense. Meaning if these were numbers that didn't have nice arcsecant values, I wouldn't do it. Right? If this was the square root of 5, I'm not changing it to arcsecant of square root of 5. That's just silly. So just something to be aware of. With just like with a u substitution, with a trig substitution, if it's a definite integral, you can change the limits of integration, but you don't have to. It probably won't come up, but it could come up, so I just wanted to mention it. All right, let us move on to the next great thing. By the way, attendance form, if you haven't done it, please do it as usual. I'm sure you're all pros at doing it. I just feel like I have to say it all the time because, but I've definitely seen the data. Lots of people are doing it, so great. All right. Partial fractions. So the real kind of big idea with partial fractions is we're going to take a complicated fraction and break it up into 2 or more smaller fractions. So what I mean by that is, for example, we could totally write 9/14 as something over 2 plus something over 7. In this case, it happens to work out that it's equal to 1/2 plus 1/7, which is 7/14 plus 2/14. Or for example, we could write 1/15 as something divided by 5 plus something divided by 3. Now the hard part here, which is going to actually be easier when we actually do partial fractions, if you try to solve the system here, like by multiplying everything by 15, you get 1 equal to 3a plus 5b. And you can totally find numbers that'll work here. In this case, I think a equal to -2 and b equal to +1 will totally work, right? Nope, I got that backwards. A equal to +2 and b equal to -1. But there's probably other numbers that would work as well, which will not be true later on. So the idea really is we're going to take a fraction whose denominator factors and try and write that fraction as the sum of fractions with denominators that are like the factors of that bigger common factor or common denominator, I mean. So here we could write this as 2/5 minus 1/3. So again, we're going to be taking fractions whose denominator factors and writing them as the sum of fractions with less complicated denominators, because fractions with less complicated denominators are easier to anti-differentiate. Let's look at the example. Let's say we want to integrate something like 2x. I'm going to change it up for let's look at this one first. 2x plus 4 over x squared plus 4x plus 3. So to see if we can use partial fractions, there are 3 things we have to check. Thing 1 is kind of silly. Is it a rational function? Meaning, is it a polynomial divided by another polynomial? Yes, it is. Great. Thing 2, is it proper? Or in other words, is the degree on top strictly less than the degree on the bottom? Also yes. And thing 3, does the denominator factor? And it certainly does. So all 3 of those conditions have to be met. It has to be a rational function whose degree on top is smaller and whose denominator factor is. And most importantly of all, before we do any of that work, we should check to make sure we couldn't have done a u substitution in the first place. And we totally can do a u substitution here. If you let u equal x squared plus 4x plus 3, your du is exactly 2x plus 4 dx. And so this integral ends up working out as the integral of du over u, which is just the natural log of the opposite value of u, which is just the natural log of the opposite value of x squared plus 4x plus 3 plus c. Now I will say, you totally could have done this integral using the method of partial fractions, which we're about to talk about. And you shouldn't if you can do u substitution. Or in other words, if you can do u sub, you should always do u sub. U sub is the easiest. Everything else is harder, in my opinion. So let's look at the problem I actually wanted to do before I remembered that I should show you, do u sub first. Let's look at the integral of 2x plus 5 over x squared plus 4x plus 3. Which definitely is not going to be u substitution. So this meets all the criteria. So what we're going to do is we're going to take our integrand. We're not even going to write the whole integral. All the work we're about to do is really just algebra. So when you see partial fractions, what you really should be thinking is, I have a lot of algebra to do. So we're going to write the integrand 2x plus 5, and we're going to factor the bottom. So the bottom factors is x plus 3 times x plus 1. And now we're going to break this up. So I should say we're going to factor the bottom. And then we're going to break this up into the sum of smaller, is not quite the right word, but we're going to use fractions, or fractions with less complicated denominators, but it's easier to say smaller. Here's what I mean. We're going to say that this 2x plus 5 over x plus 3 times x plus 1 is equal to some constant divided by x plus 3 plus some other constant divided by x plus 1. Which should be true, right? If I add these two fractions together, their common denominator is going to be that common denominator over there. So these should somehow add together. So here's what we're going to do. To figure out what the constants a and b are, we're going to multiply both sides by that common denominator. So we're going to multiply this side by x plus 3 times x plus 1. And we're going to multiply this side by x plus 3 times x plus 1. Essentially, finding a common denominator and then equating the numerators to each other. So we're going to write on the left-hand side 2x plus 5. On the right-hand side, if we distribute this, we're going to get a times x plus 1 and b times x plus 3. But what I really do want to point out is what we're really just doing is getting a common denominator on the right-hand side. You could think of this as we really have 2x plus 5 over x plus 3 times x plus 1 equal to a times x plus 1 over x plus 3 times x plus 1 plus b times x plus 3 over x plus 3 times x plus 1. Right, we're really just saying, oh, if those fractions are equal, the numerators have to be equal. So this numerator, 2x plus 5, has to equal that numerator, a times x plus 1 plus b times x plus 3.
So you're not multiplying x plus 3 times x plus 1 to like the whole thing, just to a and b?
Well, so I am multiplying this here, and when I multiply a over x plus 3 times x plus 3 times x plus 1, the x plus 3's cancel.
Okay.
And I'm left with an x plus 1.
Okay.
And when I multiply it there, the x plus 1's canceled. And over on the left-hand side, I multiplied it and the whole entire denominator canceled. Now, and what I'm saying is it's more convenient to think of it as just multiplying both sides by the common denominator, but it would be equivalent to think of it as getting a common denominator on both sides and then just looking at the numerators, right? I'm looking at that numerator on the left and that numerator on the right. Now, how to find A and B? Well, there's a couple methods to use. I'm always going to tell you that you should start off using what I call the convenient values of x, meaning these equations are supposed to equal each other no matter what x is equal to. So pick really nice values of x that make some of the terms disappear. If I pick x equal to -1, and on the left-hand side, I get 2 times -1 plus 5. On the right-hand side, I get a times 0 plus b times 2. So I'm left with a 3 equal to 2b or a b equal to 3/2. And then I'm also going to pick x equal to -3. Those are my convenient values of x. They're also the values of x that would make your original denominator equal to 0, in case you're wondering where they're coming from. But really, you're just trying to look for something that'll make one of the terms disappear. So let's see, 2 times -3 plus 5 equals a times -2 plus b times 0. Or in other words, -1 equals a times -2. Or a equals 1/2. So what this means for us is that our expression, 2x plus 5 over x plus 3 times x plus 1, can be written as the sum of fractions 1/2 over x plus 3 plus 3/2 over x plus 1. And it would totally work, right? You could multiply this by x plus 1 over x plus 1, and this by x plus 3 over x plus 3, and reconstitute that thing over there. We don't want to do that because the whole point of writing it this way is this right-hand side is much easier to anti-differentiate. So we can rewrite this as the integral of 2x plus 5 over x plus 3 times x plus 1 equal to the integral of 1/2 over x plus 3 plus 3/2 over x plus 1. And that's going to equal 1/2 the natural log of the absolute value of x plus 3 plus 3/2 the natural log of the absolute value of x plus 1. Let's see. So definitely you need to get, for this partial fraction section especially, you need to get very comfortable with integrating a constant over x plus a number, right? So just, sidebar, when you integrate a constant over x plus a number, you're just going to get that constant times the natural log of the absolute value of x plus that number. But that's going to happen a lot. And you might even have a constant multiple of x, like there might be an a times x here. If you have an a times x, you end up dividing by that a. So just be aware, that's going to come up quite frequently. So this is the general process. You're going to take your function, your integrand, factor the denominator as much as possible, and then do the partial fraction decomposition. Let's look at another example. Yeah, good. So I will say there's kind of 4 subcases of partial fraction decompositions. The first one is the one we just did, which is where all the factors are nice, x plus a thing, x minus a thing, that kind of deal. Let's look at this one here. Actually, let's look at something. So we're not going to actually do this next one. I'm just going to show you something. So let's say I was going to try and integrate, although I'm not going to, because I'm sure it's going to be absolutely terrible. 5x squared plus 1 over, let's make it really truly insane, x cubed times x minus 1 squared times x plus 1 dx. So here's the deal. When you try to do the partial fraction decomposition, what this denominator has is what's called repeated linear factors. that x minus 1 squared is a linear factor, x minus 1, that is repeated to the second power. That x cubed is a linear factor, x, repeated, being raised to the third power. And so when you have a repeated linear factor, you have to have that highest power of it and every lesser power down to 1. Meaning, here's how the decomposition will work for this particular example. We're not going to finish this one. You're going to say 5x squared plus 1 over x cubed times x minus 1 squared times x plus 1 is equal to, so I want an a over x cubed and then every lesser power. So I need a b over x squared, a c over x. And then for my x minus 1 squared, I want a d over x minus 1 squared, and then every lesser power. And then for the x plus 1, it's only raised to the first, so I only need one of those. But this would be the partial fraction decomposition for this problem. And it's kind of terrible. While we're at it, we might as well talk about the other thing that comes up. Let's look at one more. Again, we're just going to do one more decomposition. We're not actually going to solve it. But if I had, say, something like x cubed plus 5x squared plus 6 over, sure, let's make it like that. Let's say we had x to the 6th plus 16x to the 4th. Well, I didn't even factor it for you. Messed up. So if we were going to factor this one, well, is it okay? It's good. Yeah. Is it suitable, right? Is the degree on top less than the degree on the bottom? Yeah. Okay. Is it factorable on the bottom? Yeah, it's factorable. So we're going to rewrite this. Again, just doing the decomposition, not actually doing any of the solving. If I factor the bottom, I have an x to the 4th times what? Right. So the x to the 4th is a linear factor that's raised to the 4th power. You might think of it as x minus 0 if you really want to. So I'm going to have an a over x to the 4th plus a b over x cubed plus a c over x squared plus a d over x. And the x squared plus 16 is not a linear factor, and it cannot be factored. Right? There isn't anything that multiplies. Well, there's any real numbers that factor x squared plus 16. So x squared plus 16 is what's called an irreducible quadratic factor. When you have an irreducible quadratic factor, it shows up in your partial fraction decomposition, but instead of just getting a constant over it, it gets a constant times x plus another constant. So it's an irreducible quadratic factor, like x squared plus 16, or x squared plus 9, or x squared plus 7. As opposed to something like x squared minus 16, which totally factors, or x squared minus 7, which technically totally factors. It factors as x minus root 7 times x plus root 7. But technically that's factoring as far as we're concerned. You're probably not going to run into that. I just want to point out, being an irreducible quadratic factor really means the parabola never crosses the x-axis. X squared plus 16 just shifted up 16. Doesn't have any real zeros. X squared minus 7 shifted down. Definitely has real zeros. They're just, oh my gosh, irrational, right? Root 7, which is totally fine. Still considered factorable.
So why is it okay to have that in irreducible quadratic? Why is it not okay to have that?
It's not that it's not okay. It's just that when you have an irreducible quadratic, you have to add on this extra ex plus f.
Why do you have to do that for an irreducible quadratic and not for x to the 4th?
Because x to the 4th is real. Well, why didn't we have to do it for x minus 1 squared? Because really we're just having x minus 1 squared. It's a repeated linear factor. Just like x to the 4th is really, that's why I was saying earlier, it might make more sense to think of x to the 4th as x minus 0 to the 4th. It's really a repeated linear factor. It's repeated 4 times. Okay. But people definitely get caught up on that. It's like, oh, well, x is raised to really high power because they're not seeing that it's a repeated linear factor, but it is.
This works for any even
Well, so here's what I want to point out. So no, it does not. So we don't typically address higher irreducible factors. Yeah, I don't know. I'm not sure how you would address x to the fourth plus 16 beyond. It's not something that typically comes up. No, it's not. It's a sum of fourth powers, not a difference of fourth powers. It was sum of a cube is totally factorable. And so if you run into a cubic, though, a cubic always has to cross the x-axis. So you can always factor a cubic into a linear thing and then a quadratic thing that may or may not be reducible. Okay.
The reason that I'm trying to find why you have
Uh-huh.
and so just having under that.
Uh-huh.
Actually, something application.
It has, I'll give you an example in a minute here to show you kind of why it works and why it doesn't work if you don't do it that way. I don't exactly, it's kind of because the algebra works is really the not super satisfying answer. So let's look at this example. 3x minus 8 over x cubed minus 4x squared dx. Definitely, I'm thinking u substitution all the time, and u substitution definitely is not going to work here. So then I move on to be like, well, trig sub isn't an option. It looks like partial fractions is the way to go. So I'm going to rewrite my fraction, 3x minus 8, over x squared times x minus 4. And I'm going to write it as a over x squared plus b over x plus c over x minus 4. It does not matter which order you write this in. Some people might write a over x plus b over x squared plus c, or some people might do the x minus 4 one first. It doesn't matter at all. It just matters as far as like if you're looking at someone else's, making sure you know what their a, b, and c and your a, b, and c means. But order doesn't matter. And then we're going to multiply both. So I really encourage you all to remember that you're multiplying both sides by this denominator. I feel like people tend to forget it. So I'm multiplying the entire equation by x squared times x minus 4. On the left-hand side, I'm just going to get 3x minus 8. On the right-hand side, and I kind of like to draw little arrows, just distributing through. I'm going to get a times x minus 4 plus b times x minus 4 plus c times x squared. Your teacher might say that they want you to equate coefficients. That's totally fine. But what you should actually do if you're ever doing these problems is always totally use up all of your convenient values of x. So what are my two convenient values of x here? What's one of them for sure? 0. What's the other one for sure? Right. Those are all of them. So we're going to exhaust those. And then if we haven't found all of A, B, and C yet, then we're going to do something else. Hint, pro tip, whatever. If you have repeated linear factors, you're going to run out of nice values of x before you find all your A, B, and C. It's just the way it works. So if we set x equal to 0, I'm going to get -8 on the left. I'm going to get a times -4 on the right, plus b times 0 plus c times 0. So I'm going to get a equal to 2. Setting x equal to 4, I'm going to get 3 times 4, which is 12, minus 8, so 4 on the left, and 0 plus c times 4 squared. So I'm going to get c equal to 1/4. And now I have run out of convenient values of x. So my options are, I actually have many options here. One option that is pretty good if you only have one thing left to find is just to pick another value for x. Pick anything you like. So you could say pick x equal to 1 is probably what I would choose if it was an option. And then plug in your a, your c, and your x. So I'm going to get 3 times 1 minus 8 equal to 2 times 1 minus 3 plus b times 1 times minus 3 plus 1/4 times 1 squared. This still doesn't seem particularly lovely to me. I'm solving this. Let's see what I've got here. I've got -5 on the left equal to 2 times -2 is -4 minus 3b plus 1/4. I'm adding 4. So I'm going to get -1 and then subtracting a 4th. I'm going to get -5/4 equal to -3b. So b is going to equal -3 times b. So B is going to equal -5/4 divided by -3, which is positive 5/12. That seems terrible. Seems not right. Does seem not right. I feel like I made, oh, I did make a mistake. I said words, and that's the problem. I was writing a thing and then I wrote the words I was saying in my head instead of writing the words in it. So I said 1 - 4 is -3, and then I wrote 1 - 3. So really I should have 2 times -3, which is -6. And then I should have add 6, you get +1, subtract the 4th, you get 3/4. And then divide by -3, you get -1/4. Not my favorite way to do this. There's a better way, which is why I showed you this terrible way first. So typically, what I would recommend is a hybrid of this method, first exhausting all your nice values of X, and then switching over to what is called equating coefficients. So if we equate coefficients, it is almost always to our benefit to look at the highest powers of X first. So looking at both sides of this equation, what's the highest power of X? One, 2, or 3? Definitely 2, right? 2. Yeah. I've got an X squared there, an X squared there, an X, right? You have to think about if you multiply it all out, what the highest power would be. Okay, so if I look at X squared, on the left-hand side of my equation, I have 0x squared. On the right-hand side of my equation, I have a b times x squared if I multiply that out, and a c times x squared. And because these equations have to be equal to each other, no matter what values are chosen for x, it has to be true that 0 is equal to b plus c. And since we know that c is equal to 1/4, we can say that b has to equal -c, which is -1/4. And to me, that is a much easier way of finding the remaining values after you've exhausted your nice values of X.
Very often, if you're doing this, you get at least 2 of the variable things opposite of each other. You put a pattern to that.
No, it just happens a lot. Sure. So here's what I did. I looked at my equation over here. And I said, these polynomials, if they're always equal to each other, which they are, it says equals here, or for polynomials to be equal to each other, the only way for a polynomial to be equal to another polynomial is for each coefficient of each power of X to be the same. Right? If you have ax squared plus bx plus c equals dx squared plus ex plus f, you better have a equal to d and b equal to e and c equal to f. There's no other way for two polynomials to actually equal each other. So that being the case, what we're saying here is the amount of x squared on the left, which is 0, must be equal to the amount of x squared on the right. It might help if I do one more thing. Let me actually multiply this out. So I multiply this out. On the left, I have 3x minus 8. On the right, I have a times x minus 4a plus b times x squared minus 4bx plus c times x squared. So equating the coefficients, or I should say grouping the coefficients together, I have a 3x minus 8 on the left. I have a b plus c times x squared. I have an a minus 4b times x. And I have a negative 4a as my constant term. And so one way people sometimes approach this, which I think is terrible, but it's totally fine, is to just say, okay, well, b plus c has to equal 0. And a minus 4b has to equal 3. And negative 4a has to equal 8. Sorry, negative 8. And you could then find a, b, and c based on that. Negative 4 equal to 8, negative 8 means a equals 2. And then plugging in a equals 2 up here, you can get 2 minus 4b equal to 3, and you could solve for b. And then solving for b here, you could solve for c up there. This one's pretty simple to do that way, but it gets much harder if you have lots more things. So usually I would always recommend doing this stuff first, using your nice values of x, and then if you run out of nice values of x, start equating the coefficients of both sides. So that, oh, okay, well, if I look at x squared over here and x squared over here, they have to be the same. 0x squared on the left has to equal bx squared plus cx squared on the right. You look, you still don't believe me. That's all right.
Yeah, I think I'll just stick to the other method, but. For some
Well,
reason-
so I will say the other method gets, this method here gets really much worse if we have more than one more thing to find, which we will. So I don't want you to, I want you to work on believing this. So right, all I've really said here is, if I look at this equation up here, I have 0x squared plus 3x minus 8 equal to b plus c x squared plus a minus 4bx minus 4a. So
Like two coefficients of x squared.
there's one coefficient of x squared. It's b plus c. That is the coefficient of x squared on the right hand side. Just like the coefficient of x is a minus 4b. And the coefficient of, and the constant term is negative 4a. And they all equate, right? Negative 4a does equal negative 8 because a is 2. And a minus 4b does equal 3 because a equals 2 and b equals negative 1/4. And 2 minus 4 times negative 1/4 is 2 plus 1, which is 3. And b plus c equals 0 because c equals positive 1/4. And b was negative 1/4. So you could, and some people do, just rely on equating coefficients. I do not think that's the way to go, but it would work. So then back to the story that we were actually trying to figure out the answer to. We're trying to do this integral. So that integral is going to become the integral of a over x squared plus b, which was negative 1/4, over x plus c, which is positive 1/4 over x minus 4. Things that have higher powers, we have to just think about using the power rule. The antiderivative of x to the negative second is going to be x to the negative first divided by negative 1. And then we're going to get a minus 1/4 natural log of the absolute value of x plus 1/4 natural log of the opposite value of x minus 4 plus c. I will point out that you might, if you see this in a textbook, you might see someone factor out the 1/4 and combine those logarithms together. So I could totally see someone writing this as negative 2 over x plus 1/4 times the natural log of the opposite value of x minus 4 over x. I don't think you need to do that or should do that. I'm just saying that if you're checking an answer in a textbook, you might see someone write it like this because they like combining logarithms when they can. Which seems silly, but you know. Questions about this one before we do another one? Well, this next one. Oh, interesting. Oh, yeah, okay, sure. Yeah. How much time we got? We got 10 minutes. Okay, so let's look at another one. And this will get it. So you're gonna miss it, Manny, but this is gonna get it kind of, this example is gonna show why we need the irreducible quadratic factor to have an ax plus b or whatever. Sure, yeah. So let's say we want to do the following integral, the integral of x plus 1. You're welcome. Over x cubed plus x. We're definitely, I will say, we're going to talk, I imagine talking about partial fractions on Wednesday as well, because there's kind of a lot to cover with partial fractions. So let's say we have this. Doesn't look like a U sub, so I'm going to try to factor it. And the bottom does factor, although minimally. It factors as x times x squared plus 1. So I'm going to set this up as, interesting, a over x plus bx plus c over x squared plus 1. And we're going to do it, and then we're going to talk about what would have happened if we didn't do it. So let's see here. So multiplying both sides by my common denominator, as usual. On the left-hand side, we just get the numerator. On the right-hand side, we get a times x squared plus 1 plus bx plus c all times x. And here I only really have one convenient value of x to use. X equal to 0. If I plug in x equal to 0, I get 0 plus 1 on the left-hand side, and I get a times 1 on the right-hand side. So that's going to give me a equal to 1. But now I have to start equating coefficients. So it really might work best for you to multiply it all out. I don't like to do that because I'm lazy. So for example, if I was equating the x squared, I would look at it and see, okay, let me ask you all, how much x squared is on the left? If I look at this equation right here, 0x squared on the left. How much x squared is on the right? Well, you have to think about multiplying it out. So I multiply that, I'd have an a times x squared plus an a, which doesn't contribute, plus a b times x squared plus a c times x. So it looks like I've got an a plus b. But depending on the level of complexity of your polynomial, it might just make more sense to actually multiply the right-hand side and say I've got x plus 1 on the left equals ax squared plus a plus bx squared plus cx, and write it as a plus b x squared plus c times x plus a. That might just make it easier. So now if we equate coefficients, oh yeah, 0x squared equals a plus bx squared. And since a equals 1, we know that b has to equal -1. And for the coefficient x, on the left-hand side, I have a 1, x, and on the right-hand side, I have a c times x. So 1 has to equal c. And that is, in my opinion, the preferred way of doing it. You can also just pick values of x if you really want to. As the complexity increases, that method usually ends up taking more time and effort than doing it this way. So why can't we do this the other way? So why not this? Why not say x plus 1 over x times x squared plus 1 just equals a over x plus b over x squared plus 1? Well, it doesn't work. Meaning, if you multiply both sides by the common denominator, you get x plus 1 equal to a times x squared plus 1 plus b times x. And the problem here is that now we have on the left-hand side 0x squared plus 1x plus 1 equal to ax squared plus bx plus a. And the issue is that a has to be two different things. For the x squareds to equate, you need a equal to 0. But for the constant terms to equate, you need a equal to 1. And that's a problem. So that's an example of why for every irreducible quadratic factor, you can't just have a constant on top of it. You need a constant times x plus another constant to make it work. Seem reasonable-ish? Maybe? Okay. Yeah. Oh yeah, we're definitely gonna solve the integral. So solving out the integral, we have the integral of x plus 1 over x cubed plus x dx equal to the integral of a over x plus bx over c. So negative x plus 1 over x squared plus 1. And I can't imagine a time where this has ever happened or where this has never happened. You always have to break this irreducible quadratic factor piece up into two pieces. I don't think there's ever a way to not do it that way, unless it's, unless one of them is 0, but then yeah. So we're gonna write this as, well, integral of 1 over x is the natural log of the absolute value of x. And I've got plus the integral of negative x over x squared plus 1 plus the integral of 1 over x squared plus 1. And this almost always boils down to this being just arctangent and this being a u substitution. So we're going to end up getting the natural log of the opposite value of x minus 1/2 the natural log of the opposite value of x squared plus 1. Because we did a u sub where u was equal to x squared plus 1 and du was 2x dx. And then arctangent of x. So these irreducible quadratic factors typically do have an arctangent in their answer.
I just wanted to make sure I wasn't going.
No, yeah, it's very standard that happens. Fun times. Let's see what that. Here we go. We got to for one more. Let's go back. Yeah. I'm sure that's a good one. So let's look at the integral of x squared over x to the 4th minus 1 dx. And again, I just want to point out that unless your denominator factors completely as linear factors that don't have higher powers, you're always going to run out of nice values of x. You're going to have to do some of this equating coefficients or whatever. And this is going to be one of those cases because we certainly can't do a u sub. So we're going to factor this denominator as x squared minus 1 times x squared plus 1. And then we're going to factor that as x minus 1 times x plus 1 times x squared plus 1. Right, because we have a difference of squares, and then the difference of squares is another difference of squares. So then we're going to write this as x squared over x minus 1 times x plus 1 times x squared plus 1 as a over x minus 1 plus b over x plus 1 plus c over x squared plus 1. Oh, not c. What do I really need over x squared plus 1? Yeah, thank you. All right, and then we multiply both sides by the common denominator. Let's see what we get. So we're going to get x squared on the left. We're going to get a times x plus 1 times x squared plus 1. We're going to get b times x minus 1 times x squared plus 1. And we're going to get cx plus d times x minus 1 times x plus 1. Whoa, that's looking kind of gnarly. So let's utilize our convenient values of x. X equal to 1. 1 on the left, a times 1 plus 1 is 2, times 1 plus 1 is 2, and the rest of the terms should be 0. So if you're using one of these convenient values and something isn't 0, it should mean the rest of them are. And they are. 1 minus 1 is 0, 1 minus 1 is 0. Cool. So you end up getting 1/4 is equal to a. Now we're also going to pick x equal to -1. And we're going to get -1 squared, which is still 1. Equal to 0 plus b times -2 times -1 squared plus 1 is +2. So -1/4 is going to equal b. And now we have run out of convenient values. So I'm going to look for the highest power I would get on either side if I multiplied it all out. Why the highest power? Usually the higher the power is, the less terms there are associated with that. Like when you multiply some polynomial and you like multiply all the things together, you often get a lot of middle terms that have lesser powers, but usually the highest power only shows up once or twice. So that's why I picked the highest power, just because there's less to deal with. So the highest power I see that I would get if I multiplied this all out would be x to the 3rd. And I have 0 of it on the left-hand side. On the right-hand side, if I multiplied this out, would I get an a times x cubed? Good question. Let's see, if I multiply this out, that's going to be x cubed plus x squared plus x plus 1. So yeah, I would get an a times x cubed. And here, if I multiply this out, that would be an x cubed minus x squared plus x minus 1. And here, if I multiply this out, that's an x squared minus 1 times a cx plus d. So that's going to be cx cubed plus dx squared minus cx plus d. So it looks like my x cubed term on the right-hand side is a plus b plus c. But I know a and b. A is 1/4, b is negative 1/4. So I have 0 equal to 1/4 minus 1/4 plus c. So what's c going to be? Kind of unexcitingly 0. And then I move down to the next lowest power, or the next highest power.
Does that say, all the way at the end when you multiply CX plus D times X squared? Yeah, does that say?
That says cx cubed plus dx squared minus cx, and it should be minus d. Thank you. So let's look at the x squared terms now. So for x squared on the left-hand side, I have 1. On the right-hand side, I would have an a times x squared, and b times negative x squared, so a negative b, and no c times x squared, but I do have a d times x squared. So then plugging in our known values of a and b, you get 1 equals 1/4 minus 1/4 plus d, so it looks like d is equal to 1/2. Now we have all the pieces we need, we can go ahead and do the integral. So our integral is going to be the integral of 1/4 over x minus 1 minus 1/4 over x plus 1 plus cx, but that's 0. That's great. That helps me out. Plus d. So d is the 1/2 over x squared plus 1. So this ends up equaling 1/4 natural log of the absolute value of x minus 1 minus 1/4 natural log of the absolute value of x plus 1 plus 1/2 arc tangent of x.